Okay, so section 6.1 is an application of integration. So in chapter 5, you learned a lot of integration techniques, and substitution, partial fractions, integration by parts, um, uh, trigonometric integrals. I mean, you've learned a lot about how to integrate functions, and so given that knowledge, we can in chapter 6 focus on some applications now that we have the tools to handle applications. And chapter 6 is entirely about applications of integration, and section 6.1 deals with areas. So what do we mean by areas here? All right, let me go here to an application of area. Area between curves. Area between curves. So what you're used to, let me just maybe get the whiteboard here and show you here. One moment here. No, I want that. Okay, so this is what you're really used to. You have some function, f of x, and you have limits a and b, and you want to find the area underneath the curve. This is a definite integral, a proper definite integral. Okay. And how did you learn about, when you first learned about integrals and coming up with the evaluation procedure to compute an integral? As you might recall, you approximated the area underneath a curve with rectangles. And I'm sorry if these are not drawn perfectly, but you get the general idea. And all of these rectangles, of course, were bounded by the x-axis. Hold on. All of these rectangles were bounded by the x-axis below and the function above. Okay, so the height of a rectangle, okay, all right, maybe I'll put that in black. The height of a rectangle was just defined by the function minus 0, because you have y equals f of x, minus y equals 0. And that's just f of x. So in other words, all the heights of the rectangles were given by the function f of x. But you could think of that really as the height as the difference of the top minus the bottom. And that difference is f of x minus 0. Okay. And so now what we want to do is we want to extend this idea. We want to extend this idea to the situation. I can draw it maybe over here. Okay, extend the idea to the situation where you have a function f of x, okay, and you have another function, say g of x, and of course you have limits from a to b, and you want to find the area between these two functions, a function on top and a function on the bottom. Okay. Well, it's not that hard. It's not that hard to see how to do this, because if we look here at the book, I mean, in figure 1, this is the scenario that we have. Okay, a function on top, which is f of x, a function on the bottom, which is g of x, and we want to estimate the area between those two functions from a to b. So it would be logical to estimate that area just to inscribe some rectangles. The bottom rectangle starts at the bottom function g of x, as you see in figure 2 here, and the top of the rectangles stop at the function f of x. You see that in figure 2a? You see the rectangle there? How the rectangle, it's inscribed between the two curves. Okay, it's inscribed there. And the height of the rectangle is the difference between the function f of x and the function g of x. F of x minus g of x. That's the height of the rectangle. And then the width of the rectangle is delta x. And so therefore, if we were to use a Riemann sum to approximate the area between these two curves, well, I mean, of course, in part B now, we put in a lot of rectangles. And we find the area of each rectangle and add up all those areas. And that gives us what I've highlighted above. The Riemann sum, where I equals 1 to n, of f of xi minus g of xi times delta x. Are there any questions on that idea there? Is everybody, who's comfortable so far? Okay, Tao's good. Leping, wonderful. Are there any questions? Okay. Yes, Samuel.
So hold on. Can you go up for a second, a little higher up in the textbook?
Sure. Hold on, let me highlight that. A little higher up here.
Yeah. What is that? What is S over here?
S stands for, well, in the way they've defined S there in figure 1. Hold on. S is the set of all points such that x is between a and b, and y is between g of x and f of x. It's all the coordinates in the xy plane that satisfy those two constraints. And if you put all those points together, that's going to be that area S, that blue shaded area S. Because every point on that shaded area S, the x coordinate is between a and b, and the y coordinate is between f of x and g of x. And we want to estimate that. We want to find that area. We want to find that area. So how would we do it? How would we do it? Well, when you learned about integration, you learned, first of all, to approximate the area with rectangles. And so here in figure 2, hold on here. Let me get that up a little bit. Here in figure 2, you have a typical rectangle in figure 2a. Okay, and how do we find the area of the rectangle? Well, the height of the rectangle is the f of x minus g of x. And the width of the rectangle is delta x. And if we add all those rectangles together, if we put, I guess in the figure B they have 8 rectangles there, right? Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9 rectangles in part B. You would just add up those areas and we'd get an approximation. But what can we do to make the approximation better? Well, all we need to do is take the limit as n goes to infinity of that Riemann sum, and that's going to get us the true area between those, the true area of that area S between the two functions. This Riemann sum here, if you take the limit as n goes to infinity, what's that going to give you? What does that turn into? The limit, if you have inscribed rectangles and you make the subinterval smaller and smaller and smaller, what does the sum of those rectangles eventually approach? The sum of the areas of the rectangles.
Infinity?
Well, n goes to infinity, so that makes the rectangles thinner and thinner and thinner. It's going to better approximate the area. But what, do you recall from Calculus 1 what this turns into? Begins with an I.
Integral.
An integral. That's right. That's right, Lapine. This is just an integral. Okay, and so, someone has to mute their mic. Got some background noise here. Thank you, thank you. So, yeah. So if you have a region that's bounded between two curves, okay, the curves are continuous, f and g, then the area between the curves is given here by this formula. Okay, are there any questions on that? Yes, Thomas.
Sorry, this might be a little bit of a redundant question, but where did so I noticed in the formula above n is approaching infinity, so it's just becoming more and more accurate. And I noticed
Yes.
that in the equation on the bottom there's an a and a b value. So is that just like situational to each question, or?
Well, the rectangles that you made your approximation with, see there in figure 2b how the rectangles start at, in figure 2b, how they start at A on the x-axis, the A value,
Yeah.
and then end at the B value on the x-axis?
Yeah.
That's all there is to it.
Okay.
Yeah, that's where they come from.
All right, thank you.
Yeah. All right, you're welcome. Are there any other good questions? Okay, well, of course, we'll do an example, but let's look a little bit at some of the book examples here. Okay, so in example 1, okay, they want you to find the area of the region bounded above by the function y equals e to the x, below by the function y equals x, and bounded on the sides by x equals 0 and x equals 1. Those are vertical lines. So if we look at a picture of this, here's what we're trying to find the area of in figure 4. Okay, that's what we're trying to find the area of. That blue area. The function above is y equals e to the x. That looks like an exponential function. Function below is y equals x. And on the x-axis, you go from 0 to 1. Now, it looks like the x-axis, they've made the notch where you go to 1 quite a bit larger than on the y-axis. Not quite sure why they did that, but you know. So you see what they do there. You see how in figure 4 they draw a little rectangle there with a delta x? That's just telling you that you're going to be adding vertical areas of vertical rectangles, and ultimately your integral will be with respect to x. Okay, that's all that means. And so in this problem, here's the solution. Are there any questions on that? Okay, maybe give a thumbs up if you're comfortable. Okay, Tal's good. Leping and Baraka and Jazi, Marcus. Wonderful, wonderful. Okay. All right, so let's proceed on then. And please let me know if you have any questions. So figure 5 really was a situation where, you know, if we want to be a little more general here, you have a function on top and a function on the bottom. So they call that, the function on top is called y sub t, and the function on the bottom is called y sub b for the bottom function. Okay, so that's the scenario there. That's the scenario. All right, let's look a little bit more here. Let's look a little bit more. Let's look at the second example. Okay, let's look at the second example here. Okay, they want you to find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. So you have two parabolas that are going to enclose a region. So what do you think, for example, 2, that you'd have to do here to get things started? I mean, what would you have to do to help you do this problem? You haven't needed to do it too much up to now, right? But I mean, how would you start this problem? We have to identify which of these functions is the top function, which is the bottom function.
Graph them.
That's right, Sophie. We have to graph those functions. We could graph them on our TI calculators. We could graph them on, you know, a graphing software. And I'm going to actually, you know, I know that many of you use Desmos for graphing, and I want to investigate if I can get a version of Desmos that has the graphing feature on it. Not that you need it for exam 1, but for the second exam on July 1st, you know, that exam, which will be an examity, right? Like the same kind of format as your first exam. That second exam, you will need to do some graphing to help you. And I want to see if Desmos has a graphing calculator that doesn't include, like, any integral capability, But I'll worry about that later. Let's focus here on what we got here. Okay, well, if we graph these two functions, this is the picture here in figure 6. Okay, so clearly you can identify the top function as 2x minus x squared and the bottom function as x squared. Now you need to know where the functions, where this area between them begins and ends, right? Because it looks like we're going to be using vertical rectangles to help us get that area. In other words, we're going to be integrating with respect to dx. You see how throughout the entire shaded region, the vertical rectangle starts at the bottom function and goes to the top function. So it appears that the points of intersection between those two parabolas are 0, 0, and 1, 1. Okay, now how do they get that? How do they get that? Okay, well, okay, here in the solution, okay, you set the two graphs equal to, you set the two functions equal to each other to find the points of intersection. Because where the two functions intersect, they're going to have the same x values and the same y values, right? So let's find what the x values are. So set the two functions equal to each other, and you'll have x squared equals 2x minus x squared, or 2x squared minus 2x equals 0. Factor out the 2x, and you'll get 2x times x minus 1 equals 0. So x will equal 0 or 1. So x is 0 or 1, and if we put 0 and 1 back in like the y equals x squared, we'll get 0 and 1 as well. So that's how they got those 2 points of intersection. Okay. And so the total area, okay, maybe I'll just highlight it here. This would be how you find your total area. The top function is 2x minus x squared. The bottom function is x squared. And if you subtract 2x minus x squared, that's the top function minus the bottom function, you're going to get 2x minus 2x squared. Okay, so are there any questions so far? Yes, Samuel.
The problem originally said the side bounds were 0 and 1.
Well, the region lies between x equals 0 and x equals 1. You weren't given that. Hold on. Let me go back to what they state here. Hold on. Maybe I'll put it in pink. Okay. So here they state find the area of the region enclosed by those two parabolas. So they don't tell you. Well, unlike the previous problem, they don't give you a starting x value or an ending x value. They don't give you any limits. So you have to find the limits by graphing the two functions. Okay, and figuring out what the points of intersection are. And incidentally, you could use on your calculator, how many of you use the intersect feature, on like their TI-83 or TI-84? Okay, Samuel's used it, and so yeah, question, Samuel?
Oh no, I'm just trying to say that I've used.
Okay, excellent. So yeah. Are there any questions on this? The area between those two curves from 0 to 1 is actually equal to 1/3. Okay, so, you know, if you had like a plot of land, and the plot of land were, you know, in that shape there in figure 6, it could be 1/3 square miles, that area of land. Okay, land is not always in rectangles, right? So, yeah. All right, well, let's move on. Let's move on. Okay. Oh, now let's look at figure 9. This is interesting. This is interesting in figure 9. So here you have a situation where you don't have two different functions of x that are like bounding the function. You have two different functions of y. Okay, and those are functions. If x is a function of y, the functions are going to look like that. It's like if I just kind of refresh your memory here. Hold on here. So if you had the function x equals y squared, well, hold on. I can do something a little bit more here. Hold on. Okay, let me put this. Okay, so this function here, this parabola, is y equals x squared, right? Y equals x squared. Here's the x-axis. Here's the y-axis. Let me go ahead and erase that there. Okay, so we all recognize y equals x squared as an up and down parabola. But let me ask you this. What would the equation of this blue parabola be? Samuel?
Square root of x.
Well, just this part here would be the square root of x, that top part. But we want the whole function.
Square root of x minus x squared?
Well, I mean, this is what I was looking for. And thank you, everybody, for your answers. Hold that thought, Sophie. How about this? How about, hold on. I'm going to have to get out my, sorry, let me get this in blue. How about x equals y squared? And incidentally, if x equals y squared, okay, then y is going to equal plus or minus the square root of x. So as Samuel recognized, this part of that sideways parabola is y equals positive square root of x, and the bottom part is y equals negative square root of x. Okay, but the point is, so like here for y equals x squared, that up and down parabola, y is a function of x. But for x equals y squared, there x is a function of, and maybe, I'll call this F1 and this F2. But for the sideways parabola, x equals y squared, how many have seen that kind of graph maybe in one of their earlier courses? Graphing sideways parabola like that. It's something you should have seen. Sean's seen it, and Gloria, and many of you. Okay, so of course, if you use the TI-83 or 84 calculator in order to graph that sideways parabola, you need to graph y equals positive root x and y equals negative root x. Right? But when x equals y squared, that means x is a function of what variable? X is a function of so let me phrase it again. Maybe I misstated. Hold on. When y was equal to x squared, okay, you probably have no problem saying, hey, if y equals x squared, then y is a function of x, right? But now we have this situation here where x equals y squared. Hey, that means x is a function of
Y.
y. Good, good. So when x is a function of y, that's going to give us functions that go up and down. Because if you think about it, if you were to treat the x-axis as your vertical axis and the y-axis as your horizontal axis, x equals y squared would indeed be, x would be a function of y. And, we can't limit ourselves when we find areas between curves. We can't limit ourselves to horizontal functions. We also have to consider functions that are vertical functions. And so now, when we go to the ebook and we see this picture here, figure 9, you have an area. It's bounded on the left by a function x equals g of y, and it's bounded on the right by a function x equals f of y. And then it's capped off at the bottom and the top by horizontal lines, y equals d and y equals c. And so if you wanted to find the area, okay, hold on here. If you wanted to find the area, that blue area there in figure 9, you will take the difference between the right function, x of r, and the left function, x of l. You see now, it's not y of t, y sub t minus y sub b anymore. It's x sub r minus x sub l, the right function minus the left function. And you're integrating with respect to y, because look in the picture there. You see in the picture in figure 9 how they, how would you approximate the area using rectangles? You would use horizontal rectangles, right? You wouldn't use vertical rectangles. That's not going to work. You have to use horizontal rectangles. You see that? All right, are there any questions on that so far? We'll look at an example, but are there any questions? All right, let's go down here. Okay, and then there's another figure. So in example 5, so to find these areas between two functions, sometimes we'll integrate with respect to x, sometimes we'll integrate with respect to y. You can always do one or the other, but sometimes integrating with respect to one variable is easier than integrating with respect to the other variable. Okay, so here they want you to find the area enclosed by the line in example 5 here. Okay, they want you to find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Okay. So for if we were to graph y squared equals 2x plus 6, you know, how would we do that? Well, let me ask you this. Let me go to the whiteboard. Y squared equals 2x plus 6. Okay. So there, y is equal to, is y equal to the square root of 2x plus 6? Just the square root of 2x plus 6? What I'm asking is, how am I going to graph this parabola? Right, good, Renan. I'm going to take the square root and get y equals plus or minus square root of 2x plus 6. So like on my T 83 or 84, I'd have y equals plus the square, y1 equals plus the square root of 2x plus 6, and y2 equals negative square root of 2x plus 6. And I'd graph both those functions, and that would give me a sideways parabola. Okay? And this is stuff you've done. You could graph both of these functions in Desmos as well. Okay? And what you'll see then, is this particular picture in figure 11. That's what you're going to see. The intersection points can be found by simply setting the two equations. Well, you could set them equal to one another. Well, actually, that's a little bit difficult. Hold on. Let me go to the whiteboard here. So let me see here. We have y equals, so this is for example 5, and I'm really not formally, you know, I mean, this is stuff I think, this is material that I think you're, you know, is sort of like review for you. Should be review. If I want the points of intersection, I could graphically find them. That's okay. But also at the points of intersection, since both of these equations have to be true, that means then that x minus 1 squared would have to equal 2x plus 6, right? Because I'm substituting in y equals x minus 1 into the second equation, because they're both true at the points of intersection. So this is going to give me x squared minus 2x plus 1 equals 2x plus 6. and I'll have x squared minus 4x plus 1 equals 6. And then x squared minus 4x minus 5 equals 0. I subtract 6 on both sides. Okay, so here, on this step here, I added 2x to both sides of this equation. And then here, I subtracted 6 on both sides of that equation. And so x squared minus 4x minus 5 equals 0. I want to solve for x. Well, this can be factored, right? What are the factors going to be? Samuel?
Sorry. X plus 1 times x minus 5.
Good. X plus 1 times x minus 5. Good. And so this means that x equals negative 1 or x equals 5. And if x equals negative 1, if we put negative 1 back in the first equation because it's easier, I'll get y equals negative 1 minus 1, which is negative 2. And if I put 5 back in the first equation here, I'll get y, that implies that sign there, y equals 5 minus 1, which is 4. So you get intersection points of negative 1, negative 2, and 5 and 4. Those are the two intersection points. So in these problems, you have to find the points of intersection. And I know you've done that many times before. Okay, done that many times before. So what we'll do now, let's go back. And this is in the recording. This is in the recording. Let's go back to the problem. Okay, and you see in the figure 11, there, and you can do a zoom on the right to make the figure look bigger. You see the points of intersection between the parabola and a line are negative 1, negative 2, and 5, 4. Okay, are there any questions on that? Okay, now what they're doing here is they're treating the region. They're looking at a function on the right and a function on the left. The function on the right is x of r equals y plus 1. The function on the left is x of l equals 1/2 squared minus 3. Now, how are they getting that? How are they getting that? Well, let's go to the whiteboard. Let's go to the whiteboard. So originally we had, what was it? Y equals x minus 1. And then we had y squared equals 2x plus 6. Okay, so this is now y is a function of x. Okay, but we want a function. We want x as a function of y. So what we can do is we can say, well, y plus 1 equals x, and so that means the line, which is based on the picture, the line bounds that area on the right. X of r is y plus 1. On the other hand, on the right side, you have y squared minus 6 equals 2x. That means y squared minus 6 over 2 equals x. And so y squared over 2 minus 6 over 2 equals x. And so y squared over 2 minus 3 equals x. And so, well, here, here's that. The function on the left is going to be x sub l equals y squared over 2 minus 3. Okay, and so are there any questions on that before I go back to the picture? Yes, Samuel.
So wait, wait. So a little bit of rates. Is the function on the right? Actually, never mind. Never mind. Never mind.
Okay, no problem. I'll tell you what. Let me go to the picture, and then this will make because you know they in the examples they leave out sometimes these little steps because they figure you can figure them out. Let me go to the picture. Hold on. Yeah, here's the picture. And what they're going to do, there's that function on the right that bounds the area, x of r equals y plus 1. And then the function on the left that bounds the function is x of l equals a half times y squared minus 3. Function on the right, function on the left. Okay, so what they're going to do is they're going to integrate with respect to y. Okay, in other words, they're I want to say this the right way. Let me go back to the whiteboard, kind of go back and forth here as I need to, because I want to fill in some details. Let me just see here. Nope. Get the pen there. I mean, this is our area, and what they want to do is they want to inscribe horizontal rectangles. Okay, they want to use horizontal rectangles okay, that go from the function on the right, which is y plus 1, to the function on the left, which is 1/2 y squared minus 3. Points of intersection, of course, are -1, -2, and 5, 4. Now the heights of these rectangles are the heights of the rectangles delta x or delta y? What would the heights of these rectangles be?
Excuse me. Delta y.
Delta y. Good. Good, Samuel. Good, Abhidhar. Delta y. And so that means then you're going to be integrating with respect to y and taking the difference of the left function and the right function. So whenever you do these problems, it's very helpful to draw a sketch and to put in your inscribed rectangles, at least put in one of them. Okay, and so if we do that then, this is how they get the answer. They get an answer of 18. Are there any questions on this process? And we'll have some time in class for you to practice. All right, well, now they integrated with respect to y, but what if they wanted to integrate with respect to x? Okay, what if you wanted to integrate with respect to x? Well, look here in figure 12. In figure 12, okay, so again, here's figure 12. How many integrals would you need if you were to, I mean, there's figure 12, there's the area. And the area seems to be broken up into two areas, A1 and A2. Why is that? Why is that? Now, this is where you have a top function. You have a function on top, function on the bottom. So after A1, when you go to A2, the area, I don't know, they seem to have an A1 and an A2. Why? Why do you need to compute two separate areas, A1 and A2, and add those areas? What do you think, Samuel?
Because the function doesn't stop at -1. I mean, okay. Let me rephrase. The lowest value amongst all the functions is not -1. The lowest x value.
Well, so you're saying that the issue is those bottom functions, right? At x equals -1, you're seeing a change, right? The bottom, when x goes from -3 to -1, okay, when x goes from -3 to -1, on what's the bottom function in area A1 in figure 12? What's the bottom function?
-√2x + 6.
-√2x + 6. Good. Okay, and then from x equals -1 to x equals 5, what's the bottom function?
X - 1.
That's right. So it changes. So that means you need. I mean, what you'd have to do is this. If you wanted to do this with respect to x, if you wanted to compute that area with respect to x, okay, the area of A1 in figure 12, okay, that would be this. That would be from -3 to -1. And you'd have square root of 2x plus 6 minus the square root, or minus negative square root of 2x plus 6 dx. Okay, and then plus a second area. Second area would go from -1 to 5. So, you have a y of t, top function minus bottom function. The top function for that second area is still going to be square root of 2x plus 6. But, as you pointed out, the bottom function changes to x minus 1. That would be y sub b. That would be y sub b. So if you're going to integrate with respect to x, you have to add up two integrals. You have to compute each integral and then add them. And that's a lot of work, right? That's a lot of work. I mean, it's possible, and I've actually done this. For my own satisfaction, I worked it out and got an answer of 18, which is the area that they show in Figure 12. I mean, it will equal 18, but it does take quite a bit more work to add up these two areas. Hold on here. Let me just like to make things look good. Big part of math is being neat. Okay, big part of the math is being neat. Math wasn't always, maybe when I was younger, a lot younger, it wasn't always my best subject. But one problem I had was I wasn't neat with my work. When I got neater with my work, that helped me with my math, which makes sense. Which makes sense. Okay. Okay, so now you see, this is what they're showing then in Figure 12. So the point they're trying to make is that you can do these problems, you can integrate with respect to x, or you can integrate with respect to y. But usually one variable is going to be easier than the, well, sometimes it won't matter which variable you use. Okay, but in this case, it does matter what variable you use. I mean, it makes it easier to integrate with respect to y. Okay? All right, let's go a little more here then, if there are no questions. Let's go a little bit further. The book has excellent examples. It truly does. Another thing occasionally you want to do is you want to find an area that's enclosed by parametric curves. Okay, so they give an example here. They give an example. I'm going to go right to the example. I don't want to get too technical here, because the example is pretty straightforward. They want you to find, in this example, the area. Hold on. Can I make this? Can I highlight this? Maybe not. Huh? Hold on here. Okay, find the area under one arch of the cycloid. So you're used to with well, if we again, I'll go back to the whiteboard here. Okay, let me just so like if you have x equals cosine of t and y equals sine of t, okay, where t is between 0 and 2 pi, okay, those are parametric equations, right? These are parametric equations. How many recall seeing those in maybe algebra or pre-calculus? Okay, Samuel recalls it, and somebody else too. Hold on here. Okay, so that somebody else did. I got to erase. But the point is, if you let t vary, you're going to get coordinates x and y, and they're going to trace out a curve in space. So in this case, when hold on here. What would these two parametric equations x equals cosine of t, and y equals sine of t, what would they trace out? What would they trace out in the xy plane?
A circle-ish.
That's right. That's right. And you can put your that's right, Samuel. You can put your calculator in parametric mode. I assume Desmos has parametric mode as well. Okay, the full Desmos. And this would be, you know, you would start here because when t equals 0, cosine of 0 is, you know, cosine of 0 is 1, and the sine of 0 is 0. So you let t vary, and you're going to trace out, and I'm sorry my circle's not courteous, okay, but you're going to trace out a circle going in this direction. So you're used to, you know, how many find this example helpful to refresh their memories of parametric equations? Okay, excellent, Tal, excellent. Thank you, Michelle. Thank you, Baraka. All right, very good. Well, you know, in this problem here in the book, if we go back to the book now, okay, and this is why I like recordings, because I can bring a lot of things together. You know, I can bring in the whiteboard, I can bring in everything. Here you have an x and a y, but they're both functions of theta. Okay, they're both functions of theta. So in this case, the parameter isn't t, it's theta. And that's okay. You can let theta be a parameter. And what you want to do is you want to find the area under one arch of the cycloid. So the cycloid, well, in this case, they're letting r be some radius. So they're being kind of general about it. But let r be a constant. Okay, and they're letting theta, I want to be a little careful here. Theta, they're letting go from 0 to 2 pi. And so what you do here is you make a substitution. You make a substitution. Okay, so you're going to have a bottom function minus the top function. Okay, so the top function is the y equals r times 1 minus cosine theta. Okay, that's going to trace out in that figure 13, that blue area there. You know, the y there is r times 1 minus cosine theta. And yes, Samuel, yes.
How exactly do you graph that?
Well, if you put your calculator in parametric mode,
Yeah.
and you have to have like an R. Well, one moment. Let me check one thing here. One moment. Let me check one thing. One moment. Hold on. Unfortunately, you see. Oh wow. Hold on. One moment here. What I'm doing is one moment, class. Just give me one moment. One moment. Hold on. So I'm looking at Desmos for parametric equations, and it doesn't look, I mean, I think it's easier to use your graphing calculator. What you would do is you would put your calculator in parametric mode, okay? And I tell you what, class. I don't want to get hung up. This is a good thing what we have here, but let me for this last example, let me look that over with Desmos, because I would like to show you in Desmos how to do it. The homework for section 6.1, I'll leave out this kind of problem for now, okay? Because I don't want to take too much time here, you know, trying to figure it out during the lecture. So this last example, example 6, we'll keep that on ice for now, so to speak, and we'll get back to it, okay? We'll get back to it. So don't worry, Samuel, about that right now, okay? Don't worry about that one right now. Thank you for your question. Excellent, excellent. I want to do one example here with you for section 6.1. Okay. Okay, so take a moment to copy this example down. All right. And while you're doing that, checking one thing while you're copying the example down. Okay. Okay, this is great. This is great. Okay, so we want to find the area enclosed by these two parabolas. Y equals 10x squared and y squared equals 1/10 x. Okay? And so, of course, what will help is to graph the two functions. Okay? It'll help to graph the two functions. Now, which one's going to be a little harder to deal with? Y equals 10x squared or y squared equals 1/10 x? What's going to be a little harder to deal with?
Y squared equals 1/10 x.
That's right. So y squared equals 1/10 x. Keep in mind, if y squared equals 1/10 x, that means y equals plus or minus the square root of 1/10 x. And the reason I have the 10th there, I think about your homework. I know random numbers are put in. And so I want to do one that has, you know, like a 10 there. So what I'm going to do is I'm going to bring up Desmos and let's graph this particular area, okay, just to kind of get a handle on what this area looks like. Okay, so let me see here. One moment, I will bring up Desmos. And again, you don't need to graph things for the first exam, and you do have your you know, normally students do have a graphing calculator, but nevertheless, if you don't need to graph stuff for the first exam. So all right, so can everybody see the Desmos on the screen here, okay? All right, good. So, all right. And, you know, I'm definitely going to have to do a little research here and see if I can get a Desmos that doesn't, see, what worries me is I don't want the integration available, because I want you to do the integration. You're calculus students. You should be doing integrals in this class. So I'll have to see if there's a Desmos version that has the graphing, but not the integrals. So, but I'll worry about that. That's, you know, Dr. Duty homework for this weekend. But let's just try it here. So, so we got what? We got y equals 10 x squared. Okay, that's one of the functions. And then we have y equals, let's see, the square root. I just typed SQ, okay, cool, of 0.1, or I could, I guess, put in parentheses 1/10. Yeah, that'll work, 1/10, close it, x squared. Okay, that's good. And then I have y equals negative square root, there we go. See why students like this graphing. Free too, you know. Okay, so far are we good with what you see here? Maybe give me a thumbs up if you're okay. Samuel's good, and all right. So you know, I'm thinking, all right. So a lot of people are good at, and I'm thinking, okay. Yeah, question, Samuel?
Is it 1 over 10x or 1 over 10x squared?
Oh, you're right. Let me correct that. Well done, well done. All right, no problem. I'll correct that. Yep. Thank you. Thank you. Absolutely right. Okay. So let's see here. Now, what's going on here?
You gotta take away the exponents.
Oh, I got to take away that. Oh, okay. Now what is it complaining about now? Subscripts can't be.
The exponent space has to be taken out.
All
Just
right.
backspace on the, yeah.
Okay, thank you. There we go. Okay, much better, much better. Okay, so now I want the area enclosed by these two parabolas, right? And right now I don't really see an area. It looks, but there's an area there. There's an area there. So what we have to do is we have to zoom in on this. So you see on the top right, zoom in. See? There's the area right there. There's the area right there. Okay, so what's the top function? What's the top function? And let me just see here. Hold on, one moment, class. One moment. One moment. So, I mean, you know, you can, I want to be a little careful about actually shading this region. You see the region there, right? So, I mean, here it is, right? Can you see my cursor move? Like, can you see it move here? Okay, so you see the area right here. Thank you. You see the, hold on, was that in the affirmative? Was that a yeah? So you can see my cursor move, class? Did you, Tal says yes. Sophie says yes, okay. So I assume that's a yes when you're raising your hand, right? Maybe can somebody just say yes verbally? All right, good, 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 all right. Thank you, everybody, appreciate it. So here's the area. Now, what do we have to do to find this area here? What do we need to find first off?
The intersect points.
The intersection points. That's right. So, okay, that's fine. So let me see here, one moment. Okay, so I'm just seeing here. I'm trying to be honest, I'm trying to see how we get points of intersection in Desmos. Oh, look. Okay, look, see, look at that.
Yeah,
I
you can just hover
clicked
over the
there.
points.
I'm sorry?
You can just click on the dots. There's one in the up there at the other point of intersection as well. You can just click on them.
Okay, wow. Okay, there we did. There, thank you. 0, 0, and it looks like 0.1, 0.1. Those are the points of intersection. 0, 0, and 0.1, 0.1. Okay, so are we good so far? Okay, excellent. Excellent. Yeah, question, Baraka?
No, I say we're good.
You're okay. You're okay. Okay. So that's very cool. I just click on the one point. That's the one point of intersection, and here's the other point of intersection, and it gives me the coordinates. Man alive. My gosh. This is great for you guys, huh? How about that, huh? How many are loving Desmos? Okay. All right. All right. So now let's go ahead. Should we integrate with respect to X or Y? Or are both going to be equally good here? Well, they're both going to work, okay? They're both going to be equally good. So I'm going to choose to integrate with respect to X. So let me go, if I may then, let me go back to the solution. Okay, how can you tell? I'll show you, Sophie. I'll show you. Let me go to the whiteboard. And let me draw. Well, actually, let me go to the solution. Hold on. Let me go to my solution here. Okay, so the top function, so here's the picture. Here's the picture. Okay, and basically from Desmos, I can recreate the picture. So this particular area, okay, I can just as easily integrate with respect to Y as with respect to X, because the horizontal rectangles fill up the space also, and I can get away with one integral doing it. I can get away with one integral doing it. Okay, but I want to say this the right way. But the problem is, it's going to be a little more work, okay, to figure out the integrals with respect to Y. It's easier to work with the integrals with respect to X because it's just easier in this situation. It's just easier. So I'm going to choose to do it with respect to X. And so here's my integral. So really using Desmos, I just sort of did that kind of I hadn't planned on using Desmos to draw my picture, you know. I was just going to show you the picture, but I think it was valuable. How many found it valuable, that little demonstration of Desmos where we drew the picture and found those intersection points. Was that helpful? How many? Okay, Michelle likes that. Wonderful. Sophie, Jazzy, Sean, great, great. So good, good. I'm happy that it helps. Sometimes it's a little kind of risky to try things new when you're teaching a concept, because the professor doesn't want to be fumbling around in his or her lesson. But I felt it was worth trying, and it turned out to be quite simple. So I'm very happy, very happy. So okay, are there any questions on this integral? Okay, and so now this square root of 1/10 x, okay, this square root of 1/10 x here, I'm going to break that up as the square root of a tenth times the square root of an x. Okay, I can do that. You've learned that the square root of a, sorry, let me write this a little more nicely. Hold on. Hold on. The square root of a times b, square root of a times b is the square root of a times the square root of b. That's what I'm utilizing here. And I need to do that because I have to integrate. I have to integrate. And you want to be doing these integrals class now out by hand, right? Because you don't want to be using Desmos to help you get your answer for your integral. You want to be working it out by hand like you have to do on the exams, right? The antiderivative of x to the half is 2/3 times x to the 3/2. Okay, and then the antiderivative of 10x squared is 10x cubed over 3. Okay. WebAssign's going to want exact answers, right? Just like the exam in WebAssign wants exact answers, unless you're told to use put in a decimal. So I'm trying to model how you would do this. And give me a thumbs up when you're ready to go to the next page. And we'll go to the next page. All right, Maria's good, excellent. Audra's good, very good. Renad, very good, excellent. Tal's good, Baraka. All right, well, we have to put in then our limits. We have to put in these limits. Okay, have to put in the 1/10 and the 0. So let's do that. Here's the 1/10. I put that in. Okay, I put that in. So again, my function, right? I got to put in 1/10 in this entire function here, and then I have to put in 0. So here is putting in the 1/10 in the function, and here I'm putting in the 0 in the function, and then subtracting. So the first answer is going to be this. And I believe WebAssign would accept this answer because it is exact. And, you know, remember, sometimes to type in an exact answer, you need to use the calc pad. How many notice sometimes when you have a type an answer in the box in WebAssign, a calc pad pops up on the right side? How many notice that occasionally? Yeah, and what that's for, good, many of you are seeing that. What's that's for is to help you type in your answers. If there's like maybe a subscript or an x, like a, you know, x squared or something like that, you know, that it's there to help you type in things. Sometimes a Greek letter, you know, so that's why it's there. But I just wanted to, you know, simplify this. So I noted that 1/10 to the 3/2 power, okay, 1/10 to the 3/2 power is the same as 1/10 to the half power raised to the third power, because you can, you know, 1/2 times 3 is 3/2, so you multiply the exponents. So that means then I can write 1/10 to the 3/2 power as the square root of 1/10 to the third power, because of this 1/10 to the half power, then raised to the third power. And, you know, then I can work out the steps. And I end up getting 1/300. 1/300. That's the exact answer. That's what WebAssign wants. So it's a very small area, and that makes sense based on the picture, right? That makes sense. With the intersection points between the two functions were 0, 0, and a tenth and a tenth. Okay, so those, you know, the area is going to be small. I don't want you to get tripped up in WebAssign when they, you know, give you numbers with these problems. It's no big deal. You just have to, you know, work it out and be careful. But again, you know, I think WebAssign would probably take this answer. How many of you would try to get this answer at the bottom, the 1/300? How many would try to do that? I'm sure some of you would. It's good for the soul, right? Maria, how about you? Would you go that? Would you go all the way there to get 1/300?
Of course.
All right, all right. That's what I want to hear. Anybody else? All right, Sophie would. Okay, good, good, good. Are there any questions, class? Any questions on section 6.1? Okay, well, let me stop the recording.